This is an extension onto the basic differentiation rules that we learned, and what we were studying is, well, first of all, what a derivative is, and so we've been practicing ways to find the derivative, and now what we're going to be looking at is ways to apply the derivative to displacement problems and velocity and the like. So we're going to look at those applications, and then we're also going to be studying the possibility of a function not being differentiable, or you're unable to find a derivative at certain points of a function. We're going to be looking at what that situation would look like. Quick reminder, differentiable would be an adverb. It's describing a characteristic of a function, and a function is differentiable at a point if the derivative is defined at a point. So that's major. Another thing is a function is not differentiable at a point if there's a point of disagreeing derivatives. So in other words, the tangent's slopes, or the slope of the tangents, are different from the left and the right. So we're not going to go into any major proofs of this, but what I'm really hoping that you take out from the slide is that we need to be aware of non-removable discontinuities because that's associated with asymptotes. And when we derive a function that has an asymptote, it's possible that also the derivative function will also have asymptotes. And in which case, then we're going to get undefined answers or undefined derivatives when we try to plug in that certain point. So we're going to be looking for asymptotes, and we're also going to be looking for sharp points. And I'll show you what I mean in a second. So really, the stuff in yellow is what I want you to take into account here. We need to make sure that the derivative is defined, and it's not going to happen in these places oftentimes. So I'm going to take out number 75, but these are on page, this is actually information found back in your 4.1, and this is on page 264. And I'm going to go ahead and do number 67 here. What they gave you is actually an absolute value function. And this is one of those parent functions that you need to know how to graph. Normally you would start at the origin, but because we have plus 3, we're going to shift to the opposite of what you would think, back 3. Alright, so I haven't showed you how to derive an absolute value function. However, I do want to show you that we could break this into a piecewise function. And I'm going to go ahead and we're going to note that at this particular point, x equals -3, we have a point. So we should be really questioning that point and thinking it might not be differentiable there. So I'm going to write this this absolute value function as a piecewise function, and what you want to see is everything to the left of this x value equals -3. So anything x is less than or equal to -3, that's going to be taking on a slope of -1. And if you were to continue on here, you could find the slope of this line and then also the equation for this line by just taking two key points, finding the slope, and plugging it into y equals mx plus b. So I'm going to have -x minus 3, and you can even check that if you want. Here's my slope of -1, down 1 over 1. And if you went ahead and said y equals mx plus b, and then filled in a point, so let's plug in -3 comma 0, so 0 equals -1 times 3, -3 plus b, solve for your b, you would get this very same thing. Okay, so there's that line, and then let's look at this line. Alright, this is going to be those positive values, and it's going to have a slope of 3, or y-intercept of 3, so this is actually positive 1x plus 3 for all x values greater than -3. Now, if I were to say, what is the derivative as it's approaching that -3 from the left, well, then you're going to be using this function. You're going to figure what is the derivative of that particular function, and keep in mind this is -1 x to the first. Alright, and we're going to use and apply those basic differentiation rules. Take down the 1, it's going to be -1 x to the 1 minus 1, so to the 0. And then minus the derivative of a constant is just going to be 0. This derivative is just equal to -1. So f prime of x, or our function's derivative, is equal to -1 when x is less than or equal to -3. And so this would have been the left-sided limit, or left side derivative. So I'm going to go ahead and derive it What if we were approaching it from the right hand side? So this is going to be the function that I'm deriving. So again, we're just going to drop down that 1. It's going to be 1x to the 0. So in other words, just 1. The derivative of 3 is 0. So here we have contradicting derivatives. So this is what we would be saying at x equals -3. It is not differentiable. At x equals -3, it is not differentiable, or it's not differentiable at x equals -3. Also then, if I ask you for the intervals over which it is differentiable, so you could say differentiable at, and then we could say from -infinity to, I'm going to break it at that -3, and from -3 to infinity. So we've just included -3 as being differentiable for that particular function. I also want you to look at an image like this. You might come across a function that's going to look like that. Another sharp point once again, and I want you to consider if you were to draw tangent lines to this function. So here's a tangent line. As you get closer and closer to that crevice, or within that crevice, what you're going to eventually get are these vertical slopes for your tangent lines, and that's going to be undefined. So you could have derived whatever function it is, and we actually do have one like this in your assignment. It's going to be, for example, if you had x to the 2/5, okay, and you derived that function, you're going to go ahead and have f prime of x equals, and then 2/5, x to the negative, and then 3/5 is what you would get when you subtract 1 from the exponent. So in the end, what you're going to be getting is 2/5, and then you have x to the 3/5. Alright, if you were to plug in 0 into this function, f prime of 0, what you're going to get is 0 on the bottom. Okay, and that's going to get you undefined. So in which case, the derivative doesn't exist there. So again, we would have to disinclude that 0 value from an interval communication of where it's differentiable. Another application that we're going to be looking at, so besides being able to see those patterns of where it's differentiable and not, we're also going to be looking at applying the idea of derivatives to movement and displacement, and then also velocity, and then we're actually going to explore that even further. But for now, let's just focus on velocity. What we've been discussing so far is instantaneous versus average velocity, and that's a matter of looking at a tangent versus a secant. So instantaneous goes with the tangent, average velocity would go with the secant. And then also then derivatives at a certain point, that's our tangent, versus the total distance over the total time. So the change in y, the change in displacement over the change in time. So that would be that would go along with the secants. So remember when we had Brad Beebs, whatever we want to call him, remember when he was trying to get to the concert and I had this set of data up? And I hope you can see that f of x here is just x squared. What's happening is if I ask you for the average velocity, that's again just going to be average velocity after 5 seconds. So again, if this was a chart that says the distance that he's traveled given the amount of time, what you're going to be doing is saying, well, alright, after 5 seconds, using this equation, I could say the total change in time was 5 seconds, the total change in distance was this 25 minus 0. It just happens to be an easy 25. So we get 5 feet per second. Okay, versus if I asked for an instantaneous, what was his instantaneous velocity at 5 seconds? This is where you would actually have to derive the function. You wouldn't just be able to look at the data, you would actually have to have your function there. F prime of x is equal to 2x, and so that's when you would plug in what is that at particularly 5 seconds. He's going to whopping 10 feet per second at that instant moment. So I do have an example of this. This is number 78, and they're going to be giving you a displacement function, and they're going to be giving, bad typos everywhere. Find the average rate of change over the indicated interval. They've given you an interval notation of two different times, time 2 and then time 2.1. So I have gone ahead. You're supposed to compare the average to the instantaneous rate of change at the endpoints. So we're going to have to do a couple calculations here. So first of all, I've graphed this t squared minus 3, and I am going to zoom in on just this location because we're only interested in the times or the x values of x equals 2 and x equals 2.1. So when we zoom in here, sorry I couldn't get any closer, but we're looking at 2 and then, 2 and about 2.1 here. So you can see it's a very small distance that we're looking for, but if we drew a secant line, it's going to be intersecting those two points. So let's find the average rate of change between those 2 points. So if this is a line that represents displacement, we're going to have to figure out what was the y value or the location that this person or whatever this function represents was at after 2 seconds. So plug that into your function, you're going to get your y. So this is going to be 2 squared minus 3 is going to just be 1. Okay, versus this one, it's going to be 2.1 squared. That's going to be 2.1 comma and then 1.41. Okay, so that's this point right here. So if I were to ask you for the average rate of change, well, you're going to be taking the y's, subtracting those, so 1.4 minus 1 over 2.1 minus 2. So it's the change in y's over the change in x's. That's going to get you the average of these 2 points, the rate of change between those 2 points. So this is just going to be 0.4 over 0.1, and this is just going to get us 4. Okay, so if we had units, we can say units per second or whatever time. They didn't really give us a specific. So now what it also asks you is compare that to the instantaneous rate of change for the endpoints. So now what they're asking for is what was at that instant 2, what was the velocity, and what was the velocity at 2.1. So in order to do that, we're going to need to derive this function. So I'm going to find what is f prime of t, and again that's just going to be the derivative with respect to t is what we're deriving because that's our variable, so t squared minus 3. And we can apply the sum and difference rule that you can take this piece by piece. This is the power rule, bring down that 2, t to the first. Okay, and then minus a constant, so this is just equal to 2t. So that's what my f prime of t is equal to, and it will find me the slope of the tangent line at any given point. So now what I'm going to do is plug in what's f prime, or what's the derivative at, and then the 2. So this is going to get me 4, and then f prime, boo. This should have been 4, 1. Sorry. I knew something went. Okay, so sorry, when you put this in, this should have been 4.1, and I totally wrote that wrong. Okay, so this is going to be 0.41 divided by 0.1, so this is actually going to be 4.1 units. I'm sorry. So these, I mean, there was no way that these were going to be the same, so that's where I caught my error. But now let's go ahead, let me finish this off and we'll kind of discuss what I did wrong there. If you plug in 2.1 times 2, you're going to get 4.2. The instantaneous rate of change at time 2 was 4. The instantaneous rate of change at time 2.1 on the graph, so if you drew a tangent line here and a tangent line there, you can see that it's just slightly larger when you would draw the tangent line here versus the tangent line there. Okay, so bad drawing, sorry. But here you have those instantaneous rates of change at the endpoints, and then overall average, I mean, that makes a lot of sense that it's right in between the two. Alright, another quick reminder, projectile motion functions. Again, this function, this projectile motion function, represents an object that goes straight up and then of course falls straight down because of gravity. This is your gravity. This is going to be some sort of velocity in which you've thrown the ball, and this is an original height. So keep those in mind, and we are working with these in the end because we do have constant accelerations of gravity. I do have one last example that I'm going to do. It's number 82. We're going to apply our ability and our knowledge of projectile motion functions to come up with instantaneous rates of change. So for 82, a ball is thrown straight up from 220 feet from a 220 feet building with an initial velocity of negative 22. So in other words, they chucked this thing downwards. What is the velocity at 3 seconds? So notice they said velocity. They're asking for instantaneous at 3 seconds. They didn't say average. So we're going to have to assume that they're looking for the instantaneous. So first of all, I'm going to come up. We are talking feet per second, and then also 220 feet. So we are going to be using the negative 16 t squared, and then plus or minus, because they're throwing it downwards, negative 22 t, and then plus the original height, which was 220. This is going to be our height function. It gives us the height. I have gone ahead and graphed that down here. So at time 0, this is where you're standing on top of the building and you start chucking it down, and it's going to increase in its speed because of the acceleration of gravity. So what is the velocity at 3 seconds? Well, this is only a displacement function, so I actually need to find the velocity by deriving this. So I'm going to find what is h prime of t using my proper notation. And I'm also going to derive this side using my proper notation, and we are deriving with respect to t here. The rate of change of our displacement with respect to time, which is represented by those t's. So now I can go ahead, I'm just going to take this piece by piece. I'm not going to write it out, but I'm going to go ahead and say, alright, let's look at this first term. I'm going to be using the power property, so this needs to be pulled down. Okay, I'm going to get 2 times negative 16t to the first, because I'm going to drop that down, minus, I'm also going to derive this is technically to the first power, so it would bring down that 1 times 22 is just 22, t to the 0, plus, this is a constant, the derivative of a constant is just going to be 0. So h prime of t is equal to negative 32 t minus 22. So if I said what is the velocity after 3 seconds, h prime of 3 is going to be negative 32 times 3 minus 22. This gets us negative 118, and then we're going to be doing feet per second. That is my velocity. That's how many feet it's traveling in 1 second. Crazy, huh? After only 3 seconds here. It's going pretty darn fast. Alright, so what is the velocity after falling 108 feet? So in other words, let's think about this. We want to figure out what is the velocity at 108 feet. So we'll actually have to find what time that it was when it was 108 feet. So this is going to require you plugging and using in this equation that links the height, or the distance, the displacement, with time. So you're going to have to plug this in. 108 feet, so 220 minus 108 is going to be 212. So we want to basically figure out what time is it when this height was 212. So negative 16t squared minus 22t plus 220. So this is where you're going to need to use just good old algebra to figure this quadratic out to solve for the solution. So it's going to be 0 equals negative 16t squared minus 22t, and then minus, plus, cancel that out, 108. Okay, so you need to solve this, and I'm going to say you're going to need the quadratic formula. So you're going to need to find out what your t is by using that t equals opposite of b plus minus square root b squared minus 4ac all over 2a. When you find your t, you're going to get a negative value and a positive value. You want the positive value, and then whatever that time is, you're going to do the same thing. Plug it into your function that you found that will give you the derivative, or in other words, the instantaneous velocity at any given time. Alright, there are your practice problems. Good luck with those, and we'll be working on those for the next day.